In this video, we will address the topic of cache coherence. In the previous one, we talked about memory reliability. Now we are going to talk about how coherent our cache is going to be. Let's first talk about the problem and then go into the details of the problem, and then we'll talk about solutions. And the problem arises because we are sharing the cached data. So suppose you have a memory system. Over here we look at the logical view, and on the right we have a more realistic view. So for the user, it might seem like we have a very big memory system which is shared between CPU 1, CPU 2, processor 3, processor 4, and the real view is that in fact we have a very small memory, and the reality is that the CPU or the processor interacts with the cache first. So the real memory is much smaller. However, the logical memory using the virtual address space can be much bigger, or it might seem much bigger. The realistic scenario is that we have a limited memory size, and we also wanted the memory to be very fast, so we placed it very close to the processor. In fact, we placed it on the processor chip itself. So if we have a situation where we have multi-core computer system, over here we are showing 4 cores. Each of those cores will have its own cache called a private cache. So we are going to have 4 private caches over here for processor 1, 2, 3, and 4, and we are going to place that on the chip of processor 1, 2, 3, and 4 respectively, so that we have a very short access time, so we don't spend too much time accessing the data, and we have a very high bandwidth. So that's a more realistic situation over here. So what could happen if you have 4 processors that are sharing the memory? Well, let's assume that processor 1 has tried to access a memory location. Well, if it is it's not going to be in the cache, so that is going to mean that we need to fetch that into the cache of processor 1. In the meantime, if processor 2 also tries to read the same location, it's not there in this cache, the private cache of processor 2, so we bring that over here. But if we make any changes in the private caches of each of these processors, that would result in an inconsistent data, inconsistent content for that particular memory location. So that's what the problem is of cache coherence. We want all the content at every cache for that to be consistent. We need all the copies to be consistent. So because we are using multiple private caches, the copies could become inconsistent when we make some changes to that, so when write happens. This situation, the problem of cache coherence, will not happen when you have only one processor. So if you have only one processor, one cache, and one memory, they are all going to be having a consistent or coherent content. So we are not going to have this cache coherence problem in that situation. So this problem arises because we are sharing the cache between multiple processors, and we are also writing to things, so we are changing content as well. All right, so let me just quickly write the answer over here. So we know that. Okay, so let's go a little bit deeper. We'll try to see more details about the cache coherence problem here. So we are going to consider a single memory location X, and we are going to, in this table at the bottom, we are going to monitor the contents of location X, and read and that particular memory location is being read and written by 2 processors, 2 CPUs, CPU A and CPU B. And to start things off, we are assuming that neither cache for A and cache for B contains the variable, so we need to fetch it from memory, and X, the memory location X, has the value 0 in it. So as you can see, time step 0 in this table here has the contents of location X set to 0. So that's what we are initially assuming. So let me quickly highlight that here. So that's an assumption that we are making because of that initially. Then in time step 1, we are trying to read X, and the read operation is being initiated by CPU A. So when CPU A reads X, it is not going to find it in its cache, so it is going to try to fetch that location from memory, and it will bring it into cache or private cache of CPU A, and that content is now 0. The empty space over here indicates that there is no activity going on for CPU B in this case, and memory content has not changed. So it will continue to be 0 for location X. Now in the second time step, what we are doing is we are trying to read the same location X, but in this case we are the initiator is CPU B. So the second processor is initiating a read for the same memory location. If we do that, the contents of A will remain the same as before. The contents of B, because we didn't have it in the private cache of CPU B, we had to fetch it from memory, and what we fetched from memory was a 0, and we updated the cache for CPU B. And again, because we are just reading so far, the contents of location X are still 0. Now, what we are going to do in time step 3 is we are going to assume that CPU A, processor A, writes a 1 or stores a 1 into that memory location X. So what is going to happen when we write that into X? Well, when we write that, our private copy is going to change. So whatever we had for location X in the private cache of CPU A, that is going to change to 1 because we are writing 1. However, we have no mechanism in place to change the contents of private cache for CPU B. And if we do a write through cache, we will still be able to change the contents of the memory location X to stay consistent between the cache and the memory location. So we are assuming that it's a write through cache here. So after the value of X has been written by A, we see what happens. A's cache and memory both contain the new value. So that's, I guess, the good news. So the new value or the updated value in A and the memory is the same. So it's coherent at least there. However, B's cache does not have 1. Instead, it has 0 for the same memory location X. So that's a problem. And now, if B tries to read the value of X, notice what the CPU does. The CPU first tries to look at the cache. So it tries to see if the content is in the cache or not. And in this case, it is going to result in a cache hit because B, private cache of B, has the memory location X, which is 0 in this case. So it will be a cache hit and it will say it is 0, which it is not. It was supposed to give us a 1. So that's a problem of cache coherence that we have described in slightly more detail. So that's the problem. It will still receive a 0. Let's move on and let's try to define coherence. A memory system is considered to be coherent if any read of a data item returns the most recently written value. So the key word over here is most recently written value or the most updated value of the same data item. Now this definition is very simple and intuitively it might make a lot of sense, but the reality is a little bit more complex than that. So it involves a lot of aspects of memory systems that can be at play. So we come to a little bit more detailed definition of cache coherence or memory coherence. A memory system is considered to be coherent if and only if it behaves as if for any given memory location M, these three features are satisfied. So we have program order being preserved, and we have a coherent memory view, and we have write serialization. And we'll take a look at what each of these features mean in just a bit. So all these three have to be satisfied in order for us to call a memory system coherent. So let's see. The first one is preserve program order. So let's suppose we have a situation in which we have two processors, processor 1 and processor 2, that are trying to interact with certain address in memory. And over here, if write followed by read by the same processor. So in this particular example, processor 2 is not in play. We are writing to the address in memory and reading from the same address and the same processor. So write followed by the read by the same processor, assuming that there are no other writes in between by other processors, returns the value written. So whatever we write, we read the same value. That is preserving the program order. So if we relate this to our previous example, that essentially means that if CPU A were to read X after time step 3, it should see the value 1. So since CPU A was the one that wrote 1 into X, if time step 4 says CPU A reads X, it will read a 1. So that's preserving the program order. Next, coherent memory view. In this case, we have the same diagram. So we still have two processors that we are considering. We still have an address in memory. We are writing from processor 1 and we are trying to read from processor 2 to the same location. So if P1 writes X, and where X is a memory location, and P2 reads the same memory location X, P2 will see the value written by P1. You can also think of it as the updated or the new value, if that read and write are sufficiently separated in time. So there should be some difference in when that read happens. Of course, the read has to happen after we write, but there should be some separation in time for the data to get stable so that we get the correct value being read. So some separation has to be there. So in our previous example, that would mean that we would need a mechanism so that the value 0 in the cache of CPU B is replaced by the correct value or the new value 1 after CPU A stores 1 into the memory at address X in time step 3. So we need some sort of mechanism to update the private cache of other processors. That is called a coherent memory view. So we need that. We don't have that so far. If we have it, then we can call it a coherent memory. The third feature is write serialization. So this is the same diagram again. We have P1, P2. We are trying to, in this case, write to the same location in memory. So if we write, and there are multiple writes here, writes to the same location by different processors are seen in the same order by all processors. So if P1 writes first, then P2 writes second, in that case, all other processors in the memory system will see the value written in that same order. So if, say, P1 writes 10 to address X and P2 writes 20, then all other processors know that this is an old value and this is a new value. So in the previous example, if CPU B were to store 2 in memory address X after CPU A stored 1, so after time step 3, other processors in the memory system can never read the value at location X as 2 and then later read it as 1. So they will read it as 1 came first and then it got updated to 2 and not the other way around. So that's called write serialization, preserving or the processors viewing the writes in the same order in which they happened. So if all these three criteria or features are satisfied, only then we can call a memory system coherent. Alright, so that's the problem. And let's see if we can find some solutions. And the solutions could be a variety of types. So we could have software-based solutions to tackle this problem. We could have hardware-based solutions, which are far more common. And in fact, we could have some hybrid solutions, which is a combination of hardware and software-based solutions. So in software-based, there could be a compiler or runtime software support that manages that to keep the cache coherent. Or we could have instructions called flush and invalidate that help keep the memory coherent, where flush writes all or specific cache lines or blocks to memory, and invalidate instruction invalidates all or specified cache lines or blocks. And we'll see this invalidate instruction in just a bit. We are going to look at a hardware-based solution called Snooping Protocol in just a bit. So hardware-based solutions are very common, and Snooping Protocol is simple, and it's a place to start looking at what a solution could look like. So in the Snooping Protocol, we have a few situations going on. So every cache, every private cache that has a copy of the data from a block of physical memory also has a copy of the sharing status of the block. But there is no centralized state. No centralized state is kept. So let's go over this again. Every cache, every private cache has two things. One is the copy of the data that it just fetched from the physical memory. And on top of that, there is a copy of a shared status of the block that it got from memory. So that sharing status of the block helps us to establish that snooping protocol and keep the memory coherent. But note, there is no centralized state kept, so there's no global monitoring of this happening. The caches are all accessible. So caches meaning all the private caches as well as the shared status. They are all accessible via a broadcast medium. So this could be a bus or it could be a network. The third point that goes into this is the cache controllers snoop or monitor on the medium to determine whether or not they have a copy of a block that is requested on a bus. So whether I have a copy of a block that has a potential to be written onto, I will know that only by snooping on that particular broadcast medium or a bus. So let's take a look at that snooping protocol in a little bit more detail with an example. So the first point over here is cache gets exclusive access to a block when it is to be written. So the moment a private cache wants to write something to a memory location, it gets exclusive access to that particular block. Note, a block is a collection of words. So if it gets access to a block, it means that it is getting access to all the words in that particular block, so that nobody else can write to it. And then once that happens, it broadcasts an invalidate message on the bus. And this is essentially done to let all the other processors to know that the copy that they might have for that particular block is now invalid. So that broadcast helps with that. Next, a subsequent read in another cache will miss. So because we have broadcasted an invalid message, if another processor wants to read the same block, it will result in a cache miss. Earlier it was resulting in a cache hit, and it was the old value which was the problem. And the owner, meaning the processor that got exclusive access to the block, will supply the updated value to the memory as well as to other processors. So let's take a look at a scenario here. We have in the leftmost column, we have the activity, CPU activity, and in the next column we are monitoring the bus activity, the contents of CPU A's cache. So we have two CPUs here, processor A and processor B, and the contents of their caches are listed in the next two columns. And in the last column, we have the data at memory location X. So and there are two blanks over here. Those blanks are just indicating either no activity or no copy has been cached. So the first CPU activity is CPU A reads X. So when CPU A reads X, we are going to have a cache miss in the private cache of A for X. So we are going to have to fetch it from memory. So right now we have initialized the data at location X to be 0. So we fetch that into the cache of CPU A, and that changes to 0. CPU B, no activity over there, and or no copy cache there, and we didn't do any writing, so memory location X remains unchanged to 0. Next, we have CPU B reading X, the same location. So when CPU reads X, we don't have anything in CPU B's cache, so we are going to have a cache miss, in this case in the private cache of CPU B for X. Cache A remains the same. Cache B is now, or CPU B's cache is now 0. From memory it fetched 0 and it is now 0 here, and memory continues to hold a 0. And in the third step here, CPU A tries to write 1 to that particular memory location X. In this case, the moment we start writing, CPU A gets exclusive access to that particular location, and it sends an invalidate for that location X to all the other processors on the bus. And the processors, they respond by considering that that particular block right now is invalid, so it doesn't exist now. So CPU A is a 1, it has changed. Memory continues to remain a 0. We are only going to change that when we start reading something that has changed. But B, there's nothing over there because we have invalidated that particular memory line. Next, when CPU B tries to read X, what is going to happen? Well, when CPU B tries to read X, it is going to try to look at its cache, its own private cache. We are going to have a cache miss for that X because there's nothing in the CPU B's cache. And what happens if we get a cache miss? Well, we try to fetch the content from the memory, and before even that happens, CPU A, or the owner, is going to take control and is going to indicate on the bus that A actually has the updated value, and it is going to write that on the CPU B's cache as well as the memory. So it's going to update both the CPU B's cache and the memory location with the new value only when there was a read after a write. Done. Okay, so I hope we have gotten some background in this snooping protocol, and as you can see here, CPU B right now reads 1, which is the most updated value. So we have maintained the coherent memory. So all copies of X are the same. Next, there is a problem with this snooping protocol. The problem is related to the block size. So if we look at this particular scenario where we are trying to snoop, so we are going through this snooping protocol on a cache with a block size of 8 words. So a block size with 8 words, and with a single word alternatively written and read by two processors. What could happen because of this? Well, we are continuously going to exchange full blocks, all 8 words, even though we are making changes and reading to only just one word. But because this operates on full blocks, we are going to have to exchange full blocks between the two processors that are reading and writing to that word. So the problem is that that increases the coherency bandwidth demands. So the bandwidth that that is existing between the processor, the two processors, that is going to be challenged because of this snooping. And this is a problem because the block size, it is not necessarily going to be small, and if it goes even higher than 8 words, this problem can get more serious. So one solution to this could be to have a directory based protocol, so sort of a global protocol. So the solution is maintain a global view of coherent state for each block in a directory. So we are going to have to maintain a directory which monitors the coherent state for each block. And instead of broadcasting the state of the shared bus, processors send coherence requests to the directory. Then the directory then informs them what other participants care about that particular memory location. So all of this is going to mean that we have a slightly higher implementation overhead than the simple snooping protocol. However, this reduces that traffic between caches, and that means that we can scale this to larger processor counts, which have larger private caches, the number of private caches. Okay, so I hope I've given you a little bit background in this snooping protocol, and then sort of a global view that can help solve this bandwidth demand issue. All right, so with this, I think you are ready to do the class activity.